In class 12th, I will take a new topic that is very important law called the BIOT law. This is one of the fundamental law of magnetostatics. So this law was given by two scientists. One was the Jean-Baptiste BIOT and Felix SAVART. So after their surnames, it is called BIOT-Savart's law. This law was given by two scientists, namely Jean-Baptiste BIOT and Felix SAVART. In 1820. So just after the Oersted experiment, this was given by these two scientists because before, just at the time of Oersted, this was not known that how to find or how to calculate, how to find the magnitude, direction of this magnetic field so created by passing the steady current in the conductor. It is an equation of electromagnetic which describes the magnetic field. Magnetic field created by passing a steady current in a conductor. This law in magnetostatics gives a relationship relates the magnitude direction length and proximity of current. It is a fundamental law. In magnetostatics, playing the same role as Coulomb's law in electrostatics. It has a very close resemblance with amperes circuital law and Gauss law. In magnetism. So this BIOT law is one of the most important law within the limits of the magnetostatics. So this is an approximation equation within this magnetostatics. So now let's suppose we are having a conductor. Suppose we are having this conductor, and this conductor carries a current. It carries a current I. Suppose this is the point of observation, that is now P. Here we can consider that this conductor is made of a number of elements. We consider an element of length dl. Let's suppose this is an element. This is the element. This element is of length dl. And let this distance from this one is to be r. This is not distance r. So this, now we take this point now O, so this OP that is equal to r. Now we draw a circle. This is also the same as here. Let this makes an angle theta. So what we have here, this is the magnetic field, this is in this direction. Magnetic field. Here the magnetic field, that is here, this is now just downwards. This is now magnetic field B. So at all the points in this circle, the magnetic field will be the same because of this element dl. So now this whole of the wire can be divided into number of current elements. Consider a current element equal to idea. So this current element is the vector quantity. Is vector quantity in the direction of current. In the direction of current, and let this distance OP, that is equal to R. And let R equal distance of point P from current element, and that theta equal to angle between current element and distance R. This is angle theta. So this is just like this is now conductor. Suppose this we take the current element, and here this is the point of observation, then you draw a circle like this. So the magnetic field at all the points of this circle, this is now a circular path. This is a circular path. Circular path. So magnetic field due to current element at all points of circular path will be equal, because all the points from this element will be at the same distance. This is just like this is now your point, this I have taken the point, this distance R, and then this is now circular path. So all these points, whether this is now here, this is now here, this is now suppose at this here, so this will be the same one. It means that at all points of this circular path, this magnetic field will be the same one. It has the same magnitude, but its direction will be different. And you can see that on this, the direction will be just inward of this board, and here this dB is outward of this board. So the directions will be different, but the magnitude will be the same. So magnetic field at B, the magnetic field at P depends upon what? Number one, dB proportional to ideal, the current element. Second, dB proportional to 1 upon R square. So it follows the inverse square law. It means inverse square law. And that third, this dB is proportional to sin theta, the sine of the angle between this current element and the distance OP. This will be the initial. So now we can have, therefore, this dB is proportional to ideal sin theta upon R square, or this dB equal to constant K ideal sin theta upon R square, where K is constant. So this K, where K equal to constant whose value depends upon the system of units and medium around the conductor. System of units, medium around the conductor, and the material. And material of conductor. So now in case in air or vacuum, this K equal to mu naught upon 4 pi in MKS units. In MKS system, so its value is 10 raised to the power minus 7. Now this is to be Henry per meter. So this we can write here in place of K. Therefore, this dB is equal to mu naught upon 4 pi into ideal sin theta upon R square. So this is now formula. Ideal sin theta upon R square. So now you can see that this is because of the single current element, and since there are a number of current elements in the conductor, so we have to find because of the whole of the conductor, then this will be integrated over this circular path dB magnetic field due to whole of the conductor. What we have? We have to take the integration. This B is equal to mu naught upon 4 pi into integration I dl sin theta upon r square. Integration is taken over the circular path where integration is taken over circular path. So this we write down by C, eternal C. C means the circular path. I have shown you that this is not circular path. Then whatever we have this circular path, that integration will be taken over it. So this is in terms of like this one. Now this we have given the magnitude, but in terms of the vector, in vector form, now this dB, now you can have dB is equal to mu naught upon 4 pi with the vector I dl sin theta upon r square into r cap, because this is directed in the direction of the distance, this r. So we have taken the r cap, and we know that this r cap, where r cap is equal to vector r upon magnitude of this r. So this is what we have. Mu naught upon 4 pi into I dl cross r upon r cube. We can write it like this. This is now your dB. Okay. Now we can have this, but when we take the complete due to whole of conductor, B is equal to mu naught upon 4 pi integration. This is now your I dl cross R upon R is cube. This is now in this way. So you write in this way, or you write because of only the current element, then this will be written in this way. So this gives you the magnitude and direction both. The direction of this magnetic field is always perpendicular to the plane containing the current element and the vector R. The direction of B is perpendicular to plane containing current element and vector R. So this I have shown you that in case of at the point P, this is just vertically inward, and opposite to this point that will be vertically outward. So this is what the current is flowing in this way. Then the magnetic field at this point. Here this is the plane containing this current element, and this is the length. So this is now plane. So perpendicular to this one. Either this to be inward or this is outward. यानी क्या है कि जो मैग्नेटिक फील्ड होता है वो या तो इस प्लेन के परपेंडिकुलर अंदर की ओर होता है या परपेंडिकुलर बाहर की तरफ होता है. And you can easily find a conclusion from this one. Now we can have for theta equal to 0 degree or 180 degree, the V is equal to 0. It means what? That if the conductor is carrying the current, then the magnetic field along the length of the conductor is always 0. It means magnetic field along the length of conductor is always 0. So this is how this, suppose this is the conductor carrying the current. This is suppose conductor. This carries the current I. Then what we have? All the points here. At this point, this is B is equal to 0. Here, this B is equal to 0. So at all points, this is equal to 0. Here, this we have B equal to 0. So here also, if we are having the point at this one, then this B is equal to 0. So at all points along the length of the conductor, the magnetic field is always 0. And now you can have for theta equal to pi by 2 or 90 degree. B equal to mu naught upon 4 pi integration IDL upon R square, because sin 90 is equal to 1. So this is the maximum magnetic field. is maximum and this value is to be the minimum. So now we have that the maximum magnetic field is in the direction perpendicular to the length of the conductor. So suppose this is a conductor carrying the current, the magnetic field in this direction is always maximum. So when we are having the angle of 90 degree, then magnetic field is maximum. Suppose this we are having the conductor. This is the conductor. And this conductor carries a current. Suppose this is carrying a current I, then magnetic field at this point, which is making an angle of 90 degree. This angle is 90 degree, pi by 2. Then here is B is maximum. So here B equal to B maximum. Similarly here on this side if we take the point here, and it is making an angle of pi by 2, then definitely here is B maximum. So at all points which are at perpendicular distance from this one, suppose we are having this point here, then this is again making the angle pi by 2. So here this is now B is maximum. So at all points which are at perpendicular distance, this angle is pi by 2. Then here this B is maximum. So what we have? At all points which are at perpendicular distance from the current carrying conductor, the magnetic field will be maximum. Therefore, the magnetic field this we have taken now this R, this so much, this is now R. Here this is also R, here this is also now R. The magnetic field at perpendicular distance is always maximum. So this is what that we can have the direction and magnitude both that are related with this BIOT law. So this is a very important law. And also I have told you that the direction of the magnetic field is always perpendicular to the plane containing the current element and the vector R. So this is about the BIOT law. Thank you very much.